All right, buckaroos and buckarettes, I hope you recognize this. This is our home page right here. So we're going to go here to Unit 3. We're going to start with a little video here on Unit 3. We're going to go through sections 1 and 2. I believe we're going to try to do sections 1 and 2 in this video. And I think this should be helpful to you, but what I want to show you is this, not this. This is Unit 1. We don't want to go to Unit 1. We're going to go back home here. We're going to go to Unit 3. Okay? Unit 3, and what I want to show you is this Chapter 3 study guide. Okay? Now, I've already pulled it up, but I'm going to show you this Chapter 3 study guide. Also, another document I'm going to bring up is this Atomic Models History page. It's on there we're going to look at. And then when we get into Section 3, we'll pull up some of these moles to mass relationships and Section 3 quiz and so on and so forth. But right now we're going to this Chapter 3 study guide, and we are going to take a look at that thing. Okay, so that thing, hopefully, can clear up some space here, is right here, Chapter 3 study guide. Now what this thing is telling you is just telling you that you should have, ideally, you would have this study guide open. This would be open from the website. You'd have it on your page, or you could print it out if you want, or you could download it, and maybe that'd be the thing to do, is download. Then you could make notes right on the study guide. But it's going right by the book here. So it says open it to Section 1, Chapter 3, Section 1, and you read these pages. Take a couple minutes and just read these darn pages. Only 3 pages there, okay? And you want to make sure you understand this conservation of mass video, okay? Now the conservation of mass video, everybody knows what it says. It says that matter is neither created nor destroyed. All right. In a minute, we're going to get down to Dalton, talking about Dalton's atomic theory, and one of his first tenet in his theory is that atoms cannot be created or destroyed, and that goes back to this conservation of mass law. Okay. So let's take a look at it and see what this thing says here. See if we can get this baby to play for us.
This law of conservation of mass states that the total amount of matter in a closed system remains constant. In other words, matter cannot be created or destroyed during ordinary chemical reactions. In chemical reactions such as the combustion of this match inside a closed container, we find that the mass of the starting materials is the same as the mass of the ending materials. The law of conservation of mass explains why we represent chemical reactions as balanced chemical equations. The number of each atom on each side of the equation is conserved, representing that mass is conserved. The law of conservation of mass works for most things you encounter in daily life. In 1905, however, Albert Einstein showed that matter and energy could be equated with his famous E=mc² equation. The implication of this is that the law of conservation of mass will not hold for cases where large amounts of matter were converted to energy, such as in nuclear reactions. The law was revised to become the law of conservation of total mass and energy.
All right, so that's the law of conservation of mass, and we're going to see here in a second how this relates to Dalton's atomic theory. The next thing we talk about is the law of definite proportions. I'll let this video do the talking, and then I'll try to explain anything I need to there.
Table salt, sodium chloride, always consists of 39.34% by mass sodium and 60.66% by mass chlorine, no matter how big the sample is or where it comes from. The salt in the walls of a salt mine might consist of 786.8 tons of sodium and 1,213.2 tons of chlorine, but the proportion is still 39.34% by mass sodium and 60.66% by mass chlorine. A salt shaker with 100 grams of salt would contain 39.34 grams of sodium and 60.66 grams of chlorine. The proportions are still the same. A single grain of salt still contains 39.34% by mass sodium and 60.66% by mass chlorine.
So the way I keep this straight in my mind when we talk about this law of definite proportions, we're talking about different sample sizes, ENT I suppose, different sample sizes, have the same percentage of each element, regardless of sample size. Makes no difference. That's the law of definite proportions. Element. Okay? Now, we talk about this next one up here, this next law here, and this refers to, there we're talking about the law of multiple proportions. This one's a little bit more difficult to describe, and here I'm telling you that it's comparing mass ratios of elements within two different samples, okay? So that's different sample sizes in the law of definite proportion, but the same element. This is different elements, okay? So here we're talking about different elements. Different substances, okay? Let me restate that. We're talking about the same elements in different compounds. An example would be carbon monoxide, carbon dioxide. Or I think this video is going to talk about water and hydrogen peroxide, H2O2. So what the law of multiple proportions is talking about is when you have the same elements forming different compounds. Okay? See if I can get this baby to go. She's acting kind of funny here. There we go.
The law of multiple proportions states that the mass ratio for one of the elements in a compound that combines with the fixed mass of another element can be expressed in small whole numbers. This law can be demonstrated using two compounds formed from hydrogen and oxygen, water and hydrogen peroxide. A 9-gram sample of water results from the reaction of 1 gram of hydrogen gas with 8 grams of oxygen gas. A 17-gram sample of hydrogen peroxide results from the reaction of 1 gram of hydrogen gas with 16 grams of oxygen gas. We note that the amount of hydrogen in both samples is the same. The ratio of the masses of oxygen in these two compounds is 8 to 16, or 1 to 2. From this, we can deduce that there must be twice as much oxygen in hydrogen peroxide as there is in water, and the same relative amount of hydrogen in both. It does not tell us, however, exactly how many atoms of each element make up the molecule. We now know, for example, that both water and hydrogen contain 2 atoms of hydrogen per molecule, a fact we could not deduce from the law of multiple proportions, which simply told us that we had the same relative amount of hydrogen.
Okay, so again, what we're saying here is for instance, in hydrogen dihydrogen oxide or water, we're going to have 2 grams of hydrogen to 16 grams of oxygen. Okay? In hydrogen peroxide, we're going to have 2 grams of water to 32 grams of oxygen. Okay? So this equals a 1 to 8 ratio, and this is a 1 to 16 ratio. And when you compare the oxygen in water to the oxygen in hydrogen peroxide, you get a 1 to 2 ratio. And the key is that's a small whole number. And what we'll see in Dalton's atomic theory is, one of his tenets in his theory is that atoms always combine in small whole numbers. Okay? So, let's go back here to our study guide, okay, and take a look here. And so we look at Dalton's atomic theory, and what we'll see here, let's see if we can find it here. Here we go, Dalton's atomic theory. And so what we have here, this is what he says, that all matter is composed of extremely small particles. This is on page 68, by the way, in your textbook. This is page 68 in your textbook. And so what he says there is, let me go back. Whoa. What he says is that all matter is composed of extremely small particles called atoms. Well, Democritus said the same thing 2,400 years ago, okay? Dalton goes on and says that atoms of a given element are identical in size, mass, and other properties, and atoms of different elements differ in size, mass, and other properties. Well, we know we got to put this little asterisk here because of isotopes, right? Isotopes, and that's what I'm asking you on that study guide, is isotopes are atoms of the same element, but they have different numbers of neutrons, therefore they have different atomic masses. Okay, Dalton had no way of knowing that, so he's slightly got a little slight error here in his theory here. Okay, now atoms, look at that, I misspelled there. Atoms cannot be subdivided, created, or destroyed. That's his third tenet here. And we have another little asterisk here because we know that there is such a thing as fission, right? Fission, that's the A bomb, that's the atomic bomb, right? And that's where atoms are split. Atoms are split and huge amounts of energy are released. And we also have nuclear fusion. That's what happens in our sun and in the stars in the universe, where smaller atoms are fused to form larger atoms. So this is not exactly technically true either. But for our purposes, we don't get into nuclear chemistry, so for our purposes we can work with these tenets. Okay. Now number 4 says, and it's sort of a, in my mind, number 1 and number 4 kind of go together. You could just put a comma there and say, that all matter is composed of extremely small particles called atoms, and atoms of different elements combine in simple whole numbers or simple whole ratios to form chemical compounds. So what we're talking about here is the laws of definite proportions and the laws of multiple proportions. So you need to go back at the beginning of the chapter and make sure you can restate those and understand those. But that's the empirical evidence or the scientific evidence that Dalton used to state this theory right here. And so here, when we say atoms can't be destroyed, can't be created or destroyed here, 3, that kind of goes with 5, really. In a chemical reaction, atoms are combined, okay? They're separated or they're rearranged, but they're not created and they're not destroyed. Okie dokie. So that is Dalton's atomic theory, and let's see where we are here. Okay, so we go back to our study guide here, and you see that these two exceptions that I'm talking about back here, let's see where we are here. These 2 exceptions that we're talking about, I use a different color here, is number 1, isotopes, and number 2, nuclear reactions. And nuclear reactions fall into 2 categories. Either fission, that's where you split atoms, or fusion, and that's where you combine atoms. Fusion. That's what happened in the sun. That's what's happening in our sun, and this is what happens in bombs up here. Okay? So now that pretty much takes us in through section 1 of chapter 3, and that ends on page 71, and you got a couple section review questions there on page 71 that you want to answer right here. This is what this study guide's telling you, is go to those section review questions and answer those. It says list the main points of Dalton's atomic theory. Well, we just did that. what chemical laws can be explained by Dalton's theory? Well, that'd be the law of multiple proportion, the law of conservation of mass, and the law of definite proportions. Let me put them in the right order. Law of conservation of matter, the law of definite proportions, and the law of multiple proportions. And that critical question there, number 3, what you do is you just divide those to the smallest whole numbers, and you get a you come out to 1 to 2 to 4 ratio, which is small whole numbers. Okay. So now we go into section 2 in chapter 3, and it starts on page 72. And what we got to remember is, if we look at Dalton's atom, okay, when we look at Dalton's atom, we're looking at, it's really not much of a description, okay? He just says that these are small, extremely small, indivisible particles. That's all he says. He doesn't know anything about subatomic particles. He doesn't know anything about, any other subdivisions. He just says these are small particles. And I'm going to draw this bigger than a dot, because when we get to these new models, we're going to have to make some adjustments. So this is he puts his theory out here, I believe 1808. Okay, in 1897, a fellow named Thomson comes along, and he is working on this cathode ray, with this cathode ray. Now the cathode ray, what it is you have this sealed glass tube, and you have a way of putting a positive electrode in there, and that would be called the anode, and the way you put a negative electrode in there, and that'd be the cathode. And now when you turn the power on, well, let me back up. And so what happens in here is you vacuum everything out of this tube, so there's absolutely nothing in it, and then you introduce one and only one element. Seal it up, so now you know there's nothing in this tube but atoms of the same type. You turn the power on, and whoop, you get this stream of light that seems to be running from the negative pole, from the cathode to the anode. Okay, and that's why it's called a cathode ray tube. Okay. Now, Thomson was able to put this experiment together, and what we have here is a little explanation of what's going on.
When the cathode and anode of a cathode ray tube are connected to a voltage source, electric current flows through the tube and can be seen as a cathode ray. The cathode ray is made up of electrons. When a positive electric field is placed next to the tube, the path of the electrons moves toward the field. Using the strength of the electric field and the amount of deflection, J.J. Thomson was able to calculate the ratio of the charge of electrons to the mass of electrons. Imagine a baseball player throwing a ball. Like the cathode ray, with no outside influences, the ball goes straight when the baseball player throws it. A strong wind, however, could blow the ball and make it go off course. An outside positive field attracts the electrons in the cathode tube and makes them go off course. If the baseball player threw a lightweight plastic ball instead of a regular baseball, the wind's effect would be even more evident. The mass of the ball is one of the factors that determines the path the ball will take. Similarly, if the wind were stronger and the baseball player used the original ball, the wind's effect would be more evident. The strength of the outside force is one of the factors that determines the path the ball will take. By observing the path of electrons in the cathode tube, Thomson was able to calculate the ratio of charge to mass of an electron.
Okay, so you understand what's going on here. What we're saying is that when he turns this thing on, these negative particles are moving from the anode. From the cathode to the anode. Okay. When he subjects it to this positive field down here, what happens is he's able to pull these things down this way. So he knows they're negative by the fact that they're moving to the positive pole, but now he's able to make a calculation as to the size compared to the charge. When he changes this, this positive field, when he strengthens or weakens this positive field, he pulls these things. If he increases the charge here, the positive pull here, he pulls them down farther. If he decreases it, they don't get bent as much. And so from that, he's able to make a ratio between the mass of the electron and the charge. But the main thing is now he knows that this atom has got negative particles in it. Okay, he says it's got negative particles in it. Well, when he turns the power off, the particles in the tube, the complete atoms, are neutral. So there must also be positive charges in there, right? And then Goldstein and Chadwick and whatnot, they're working on other subatomic particles, and they say, well, hey, when you take the mass of the protons and you add them to the tiny, tiny mass of the electrons, you still don't have all the mass of the atom, so there must also be some neutral particles in there, okay? So now what we have is a new model of the atom that shows positive, neutral, and negative particles all in the atom. They had no idea about the arrangement, you know, where these things were, so they just stuck them in there randomly. And what they did is they called this thing the plum pudding model. And plum pudding, most people don't know nowadays even what plum pudding is, but it's like fruitcake. They just stuck these things in here, okay? And this is 1897, and this is J.J. Thomson, okay? So we come back to our study guide here, and we look at this, and we see this fellow named Millikan, Robert Millikan, 1909. He's working with electrons as well. Now what he's able to do is he's able to calculate the charge of these electrons like this.
In Millikan's oil drop experiment, he squirted negatively charged microscopic droplets of oil into a chamber and observed them with a microscope. Voltage applied to metallic plates within the chamber allowed him to create an electric field, which had an effect on the droplets. By adjusting the electric field's strength and direction so that it pushed the droplets against gravity, he could suspend the droplets. By knowing a droplet's mass and the strength of the electric field needed to suspend it, he calculated its charge. Testing several droplets in this way, he found each droplet's charge to be a whole number multiple of 1.602 times 10 to the negative 19 coulombs. This is the charge of an electron.
Okay, pretty clever experiment. He didn't actually get down to the charge of individual electrons, but he knew that there were multiple electrons on these oil drops, and what he looked for was the smallest common denominator, and what he found out was this was the smallest common denominator. So the total charge on the oil drop divided by this number always gave him whole numbers. So he knew the charge. He calculated the charge on the electron. Remember, Thomson was relating the charge to the mass. He didn't actually come out with the mass of the electron, but he was able to relate the charge to the mass. Okay, Millikan is focusing on the charge. So this comes up. This brings us up to the plum pudding model. Okay, and what I'm trying to show you here is we've got these models. These are kind of crude drawings of them, but we have this model here. We're just saying Dalton really didn't have a detailed idea of the atoms. He just knew they were small particles. Thomson comes up and shows us this plum pudding model with the protons represented by the positive particles, the neutrons with the neutral zero particles, and the electrons with the negative charge. Okay, now we come over here and we go back to our study guide, and we start to talk about Ernest Rutherford. Now if you look on page where are we? It'll be page 74, where we start talking about Rutherford's experiment. Okay. Okay, so this is Rutherford's setup, and what you have here, what we're trying to look at, what we're trying to show you here is this is gold foil. This is a piece of gold that's been hammered down into very, very thin, and he figured it down to, you know, just a few layers of atoms. Okay, inside here he had what we call alpha particles. Let me put this in here. An alpha particle, and an alpha particle What happened to my thing here? An alpha particle is a, let me get rid of this here. Okay, here we go. Let's see if this doesn't work. Alright, so we got this alpha particle, and this alpha particle has 2 electrons, it has 2 neutrons, and it has no electrons. So it's got a 2+ charge. This is actually a helium nucleus, okay? So it'd be 2, 4, and a 2+ charge, which is a pretty big, pretty big radioactive particle. But what happens is here we've actually got another box in there like this with a little slit in the front, and so this alpha particle, and there's a slit here, this alpha particle comes out of this box right here and through this box right here and travels a straight line to that gold. Now this film right here that surrounds the gold foil, this film will show every time one of these alpha particles hits it. It's like photographic film, and it will be a little spot will show up on the film when he develops it. So Rutherford, what he figured he was going to do is do a calculation on the size of these atoms, and he was shocked in what he found out. Let's see.
Ernest Rutherford, with Hans Geiger and Ernest Marsden, discovered the nucleus of the atom using a beam of positively charged alpha particles. They bombarded a sheet of gold foil with a stream of alpha particles. Most of the particles passed straight through the foil. About 1 in 8,000 particles, however, were deflected, sometimes directly back at the source. Rutherford explained these results by hypothesizing that nearly all of the mass of an atom is concentrated in a very small volume called the nucleus. If the nucleus were small, it would be easy to miss. Alpha particles which miss the nucleus are deflected only slightly, if at all. Alpha particles which hit the nucleus are deflected severely.
So, what he's saying there, in addition to what she obviously stated, is that also when these particles come by here like this, see if it stays on, they come by here like this, and even get near the nucleus, they get deflected off a little bit, you know, like this and like this. And that's because these are positive and this nucleus must be positive. Okay, all the protons are in there, and these are positive charged alpha particles, and so when they get even near the nucleus, they get separated apart. However, when they do hit the target, wham, they come off almost directly repulsed, which means this thing must be very, very massive. Okay, so Rutherford, when you hear the name Rutherford, where is he? Where is his name? Rutherford. When you hear the name Rutherford, you think, number one, the nucleus. Nucleus exists. This is a guaranteed test question. There is a nucleus. Okay. Number two, it is incredibly small and therefore dense. And number three, it's positive. It's got a positive charge. Okay, because that's where the protons are. Okay, those are the 3 things you get out of Rutherford's gold foil experiment. Don't forget them. Okay. All right. Let's see now. What do we get here? We go boom, boom, boom. Come back over here and go here. All right. So again, these are the 3 things you want to get from Rutherford's experiment. Okay. Number 1. Nucleus. Atoms have a nucleus. The nucleus exists. That's number 1. Number 2, it is small and therefore very dense. We'll talk about how dense here in a minute, okay? And then number 3, it is positive. It's positive because that's where all the protons are. Okay? All right? So now, remember we had Dalton up here. We had Dalton with this nondescript atom. Then we had Thomson with this plum pudding atom that showed the protons and the electrons and the neutrons in there. Okay? Positive, negative, and neutral. And then we have Rutherford, who shows us that this all of the mass of this this atom exists in this tiny nucleus. Okay, this is the protons plus the neutrons. Okay, the electrons are out here on the outside. Okay, all right, now let's take a look at this little video here and see what this thing tells us. I think it might be easier to go here, parts of the atom right here. So what we're saying here, this is if you saw this image on a test, this would be Rutherford's model of the atom. Okay, and so in the nucleus we have all of the positively charged center of the atom. Okay, so it contains, when we say most of the mass, it's something like 99.9%. all right, now these green and blue balls here, the green represent the protons and the blue represent the neutrons. Okay, that's in the nucleus. So this whole thing is positive. Okay, this whole nucleus is positive, and the electrons are out here orbiting in orbital energy levels outside the nucleus. Got it? Let's see what this thing says.
Parts of the atom. The electron cloud is the region surrounding the nucleus of an atom where electrons are likely to be found.
Okay, inside the nucleus again are the protons and the neutrons. Outside the nucleus are the electrons. Okie dokie. So now we look at these nuclear forces, and what we find out is, well, we'll let this lady read it to us.
Nuclear forces. The interaction that binds protons and neutrons, protons and protons, and neutrons together in a nucleus is called the nuclear force. In stable nuclei, the nuclear force is stronger than the electric repulsion between the protons alone and holds the nucleus together. In unstable nuclei, the number of protons and neutrons is not balanced, causing the nuclear force to weaken and the nucleus to decay.
That's a pretty little interesting fact about the unstable nuclei. So those are in the larger and the heavier metals, and what happens is you can see that the ratio of neutrons to protons gets much higher in those heavier metals. In our lower metals, in our lower elements, lower numbered elements, the number of neutrons is pretty closely matched to the number of protons, and that apparently gives it stability. But this attraction that holds this nucleus together is considered to be one of the strongest forces in the universe. And the way you should think about it is, what happens when you split a nucleus apart? Well, you have an atomic explosion, which is huge amounts of energy released. Well, that energy is directly proportional to the amount of energy with which that nucleus is held together. Okay, so it's a big force. It's not completely understood even today. Okay, so this should take us through, let's see where we are. This should take us through section 2, okay? And we've got a couple little notes right here. And so if you look at the typical size of an atom, then what you're saying here is that what we're saying here is that a nanometer, remember we're talking 40 and 270 picometers. Well, remember, a nanometer equals 10 to the negative 9 meters. A picometer is 10 to the negative 12 meters. So we're talking some pretty tiny stuff here, okay? Now, if you take this nucleus, okay, we're talking about 1,000th the size of the typical atom. So if you take this nucleus, for instance, any element you can think of, the masses of these elements are known pretty well. If you take that density and divide it by 1,000, right, you're talking incredible masses per cubic centimeter. This thing calculates down to 2 times 10 to the 8 metric tons. 2 times 10 to the 8 is 2, and then let's see, 2 to 10 to the 6 would be 2 million. 10 to the 7 would be 20. So that's 200 million. 200 million metric tons. A metric ton is equal to 1,000 kilograms, or 2,200 pounds. So it's just phenomenal. It's incredible the amount of mass that's calculated to be there. And your first reaction, or my first reaction, is to say, well, that's ridiculous. There's nothing that dense. But this Rutherford's experiment has been repeated and repeated and repeated thousands and thousands of times and investigated, and the evidence continues to show up to be that this is true. This nucleus is this small, and therefore it is that dense. Okay, so now theoretically in your textbook, you read along in your textbook, and focus on the reading, pay attention, and we should be somewhere around the end of chapter 3, which would be page 76. Okay, so you look at page 76, and here we are here, and somewhere it should tell you to answer these section review questions on page 76. Now, if you've got this thing, downloaded on your computer, you can just add space here and put your answers in here, put them in a different color or whatever. But the first one says define each of the following: atom, electron, nucleus, proton, neutron. Well, you have those. Atom is the smallest indivisible particle of matter. Electron is a negatively charged subatomic particle outside the nucleus. The nucleus is a tiny, small, dense, and positively charged area of the atom that contains all of the protons and the neutrons. The protons are the positively charged particles, and the neutrons are the neutrally charged particles. Number 3 says talk about these 3 scientists and what they did. Well, J.J. Thomson, 1897. It's cathode ray tube, and he gets credited with uncovering the electron. Millikan, well, Thomson, he not only uncovered it, but he also made a calculation as to the ratio of the mass to the charge. Millikan comes up with deciphering the charge on the electron. And Rutherford, you say nucleus. Rutherford is the guy who figured out that these atoms contain nuclei, and in the nucleus of each atom is almost all the mass. Okay, and that is because the nucleus contains the protons and the neutrons. Since the protons are positive and the neutrons are neutral, the entire nucleus is positive. Okay, and then why is the cathode ray tube connected to a vacuum pump? Well, that's because we have to get that. We have to get the pressure very, very low, because the charges won't flow otherwise. Okay, and we don't want a lot of unknown substances. We don't want a mixture, like a mixture of air in there. We want to isolate the individual elements. Okay. Okay, so this should get you through section 2, and we'll work on section 3 here in a little while. Now, section 3 is going to go back to numbers, as you can see. Okay, we're going to talk about the parts of an atom first, then we'll talk about isotopes, then we'll learn how to calculate average mass, and so on and so forth. But for right now, you need to make sure you focus on sections 1 and 2 in chapter 3, and if you have any questions about any of those practice problems or section review questions, be sure you bring them up in class. Okie dokie. Alrighty. Thank you, and good night.